Hello, am I audible?
Yes, yes.
Okay. Uh, let's wait for a few minutes and then we'll start.
Okay.
So, when was the second assignment deadline?
It's not second, I guess. It's third.
No,
It's on 11th.
okay, so second has already passed. Okay.
Yes, yes.
Okay, maybe we can start. So, in this third week's lectures, and I think so, there is a kind of disconnect between the third week's lecture and assignment. So this Ginsburg-Landau theory was done in the second week lectures, and then third week the assignment is mostly based on that actually. There are few lectures in the third week like spin interaction and so on, which is I don't see any questions from there. Okay. Anyway, so we'll mostly do Ginsburg-Landau theory for today, and then we'll discuss some of the questions. Okay, so Ginsburg-Landau theory is a main field level phenomenological theory. So, and it is to describe the second order phase transition actually. Okay, so what we have seen uh, in earlier lectures is that so the lectures were trying to formulate microscopically what is really happening. I mean, in terms of given that we have electron-electron interaction mediated by phonons, basically an attractive potential, then how can there be superconducting gap and so on, right? So essentially, how do we define superconductivity, or if a material is showing superconductivity? Is that, of course, experimentally thinking, your resistance is going to zero, right? At some temperature, let's say. You have some resistance and it suddenly drops to zero, right? Uh, in terms of theory, let's say, or yeah, in terms of theory, you can say, or even the experimentally also, definitely we can measure the superconducting parameter, the parameter which is kind of, uh, I mean, finite in this phase, in this particular phase, which is superconducting phase SC, and this is somewhere TC, critical temperature, is that one is the gap parameter, right? Superconducting gap parameter. And this was only finite in, I mean, whenever we had T less than Tc, and when T greater than Tc, it used to be normal metal. So delta was definitely zero, right? Normal metal means you have a band structure, something like will be, I mean, so suppose you have a band structure which will be something like this. Okay, so this, let's say, energy, and this is momentum, and anywhere you put chemical potential, you will always have some density of states to conduct. So these are, let's say, Fermi energy, different Fermi energy position, and each point you will have some density of states, so that it is metal, right? Meaning once you supply some electric field in the material, there will be conduction. Now, in the superconducting phase, there is a development of gap phase below Tc. So this you can kind of think of as a order parameter. So this is dictating that is this material ordered in the superconducting phase or not. So that's one way to kind of I mean, talk about superconducting phase. Now, this Ginsburg-Landau theory actually developed initially. It was sort of developed as a general formalism to describe second-order phase transition, uh, and 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 the most intuitive way to understand how this uh, I mean this thing explains the concept of order parameter is inbuilt into the Ginsburg-Landau theory is to consider a ferromagnet, let's say. We'll come back to superconductor very quickly, just for introduction. So let's start with some ferromagnet. So suppose we have some material, and in ferromagnet you have a macroscopic magnetization, right? So there can be a domain in the material where spins will be localized, spin will be along different direction, uh, slightly different direction. That is allowed, of course, but overall you will have a net magnetization which will be non-zero. Okay, so this I am talking about ferromagnet. So which have a net non-zero magnetization. Okay, and if you increase the temperature of this ferromagnet, and again you will see that at some temperature this magnetization will be actually zero. So all the spins here will be randomized. I mean, they will I mean orient along random directions, and as a result you will find that m equal to zero. Okay, so what this essentially tells us is that if you plot magnetization versus temperature of a ferromagnet, then you will see something. Uh, Suppose you are this below Tc. So here Tc means Curie temperature for a ferromagnet. Uh, so Curie temperature. Now you'll have some magnetization, let's say. I am not showing the behavior of it. How does it go? I'm just interested in its value. So it will have some value below Tc, right? And then it will be actually zero above Tc. Okay, so that's how we can think of, I mean, the concept of order parameter. Now, what Landau proposed is that, I mean, so what he proposes is that mean field theory, where we can understand this behavior of order parameter and the concept of order parameter in a system where there will be a second order phase transition via some thermodynamic potential. Okay, so he generally wrote a thermodynamic potential which will have some internal function, which will be a function of some internal. So for ferromagnet, it will be magnetization, it can be function of temperature and so on. There can be other parameters as well. Okay, and his proposal was that free energy, so this is the free energy we call it, but it is essentially actually thermodynamic potential. It can be gives free energy, or for that matter enthalpy. It depends actually. Okay, what you talk about in the particular setting. So this is thermodynamic free energy in the ordered phase, let's say. Okay, so in the ordered phase. Okay, so what he assumed or actually proposed is that this free energy can be expanded around whenever this order parameter is small. So m is small. So whenever this m is small, it can be expanded order by order. Okay, so it's kind of perturbative expansion. So then we can write m dot m. I'll explain why we are writing like this. And then beta by 2. This is just a convention. Alpha, beta are constants. M dot m square, and then higher order terms are there. It should be, yeah, cube and so on. Okay. Now, why we do not take linear in M, let's say, right? So linear M and cubic M, these are not considered because of symmetry regions actually. Okay, so one easy way to understand is that, let's say, so m cube are ignored. Okay, okay, so why we do not consider linear and cubic and higher order terms is that definitely as we go higher and higher order terms, so m cube, m to the power 4 and 5 and so on, because it assumes that m is small. Okay, that means we'll have I mean the higher order terms is going to be I mean suppressed as you gradually go on. Now why don't we take So this we can write small as m is very small already. And then why don't we take linear M? Because this can be thought of in the following way, that suppose you have a ferromagnet which have isotropic ferromagnet. Okay. Now the order parameter is M is definitely a three component vector. So it will have Mx, My and Mz. Okay. And this free energy must be invariant under the rotation of M because of isotropy, let's say. So this is a phenomenological model. This I mean assumes a lot of things, but it explains in a in a very simple settings how the behavior of M around temperature, around transition temperature and so on. Okay. Now it turns out that if you take that linear M term, so this will destroy the isotropy of the free energy, and free energy is a scalar quantity. That's why you see that this comes as a M dot M. Okay, so dot product. So it's not a vector product. It cannot be vector. Free energy is essentially an energy. Okay. Okay, so that's why the linear terms are not included in the free energy. Now, what people have did, it can be shown actually for even for the ferromagnet case, that so if you plot this including up to this term actually, m and m square, so there will be, so this is F free energy and then m. And now whenever you are greater than t equal to Tc, if you solve this particular sorry. So if you solve this particular free energy up to this term, then what you will get is that an above Tc, let's say. So this will be something like this. And then at t equal to Tc, we'll solve for superconducting case actually. So this will touch at some point. So this is for t equal to Tc. And then we'll have, if t is less than Tc, then this will be the case. Okay, so this should be at the same energy actually. So you will have a two degenerate points where the free energy is minimum. Okay, and the ferromagnet chooses one of these minimum energy configuration. So this is, let's say, the plus m configuration and this is minus m configuration. So you have a ferromagnet, and now, so this, the ferromagnets where the magnetization can be like this, or it can also be minus M, right? Just the opposite direction. Now, in both these configuration, there is no energetically, they are not different. Okay. So what this predicts is that once you have a ferromagnet below Tc, T less than Tc, you are either in this ground state minus M or in this ground state plus M, and it's perfectly degenerate in the energy space. Okay. Of course, in realistic system, you have a anisotropy energy and so on, so that there is, I mean, uh, there is always a preferred direction of M in real materials. So those things are not considered in simple Landau theory. But what this already tells you is that you can think of this transition of a magnet or a ferromagnet, that once you are below Tc, there is a development of finite magnetization, and once you are above that, there is no magnetization. So you can think from this particular simple free energy perspective. Okay, so we'll follow more of it. How do we get this kind of curve mathematically? Now, so this was for the case of ferromagnet. Now, what is the case for superconductor? So for superconductor, we'll deal with a, uh, I mean, complex wave function. Okay, so superconductor order parameter for Ginsburg-Landau or Landau theory actually. is coherent wave function, rather superconducting wave function. So psi, we have some phase psi 0 e to the power I phi, let's say, and the order parameter we define is represented by the psi square equal to or it's kind of proportional to, because dimensionally they are not same, so proportional to ns, and ns is the superconducting density, I mean Cooper pair density actually. So it's kind of electron density, but then Cooper pair have two electrons, so it's better to call Cooper pair density. Okay, so this will be the order parameter for Landau theory in this case. Okay, so similarly, then we'll have free energy as alpha mod psi square plus beta by 2 mod psi to the power 4. Okay, okay, and we are ignoring the higher order terms, so higher order terms are ignored. Okay. Now, so there will be, so these alpha and beta are constant, but we need to take some assumption or some actually sign convention for these two. It turns out that we need to take, so if actually two scenarios can happen, one is alpha greater than 0 and second is alpha less than 0, right? And beta always has to be greater than 0. We'll always assume beta is greater than 0. Now if beta is less than 0, let's say, then we need to take higher order terms actually. So suppose if beta is less than 0, then we need to take the psi to the power 6 term. Okay, psi to the power cube term is again we can discard because the free energy should be analytic. So del f del psi will go as psi plus I mean, okay, actually psi to the power 5 term we cannot ignore by this, but psi to the power sorry, so so the all the odd terms, so for example psi and then psi cube and then psi to the power 5, we can again apply this logic here. The magnetization is kind of isotropic, so so we should discard these odd terms. Okay, so here it will be uniform superconducting wave function, let's say, uh, and then you will see that for higher order superconductor, or let's say unconventional superconductor as we call it, those there can be wave function which are not uniform, as in the lecture we have seen, but those things are not explained in terms of simple Landau theory. Okay, and in fact, we do not have really very precise theory of ITC superconductor or unconventional superconductor. Yeah. Okay. So I was talking about what happens if beta, if you take or if you take beta less than 0, right? So if you take beta less than 0, then I need to take psi. Okay, so I need to take psi to the power 6 term. So that is because there can be a chance, depending on the values of alpha and beta, that it can be free energy itself can be less than 0, but that is not allowed actually. Okay, so that's why we assume that beta is, I mean, greater than 0. And all of these are allowed at a theoretical level because we are essentially constructing a phenomenological model to understand the behavior of superconducting order parameter, how it behaves around the transition temperature and so on. Okay. Yeah. Of course, I mean, for explaining real materials, we will always try to solve BCS theory and more con advanced actually mean field level theory and so on. Okay. Okay, so another thing I actually forgot to tell you that why we can expand this. We are often saying that psi is small, and that is because the Landau theory, I mean, only works around the T equal to Tc. Okay, so you had, I mean, let's say psi, this is psi, or I can talk in terms of m as well. So this is, let's say, Tc and then T. So Landau theory only worked around this regime, let's say, so around this particular regime. Okay. Uh, Whenever you are, I mean, T is very, very less than Tc, so you have a significant value of M, then you need to take into account of all the higher order terms as well. Okay. So those theory then is going not going to work for the Landau theory case. So we are only concerned about the T is around Tc, and as at Tc psi has to vanish, or for that matter M has to vanish for a ferromagnet. That means that around Tc M needs to be small, right? So this is the physical motivation behind choosing M, or for that matter psi for superconductors to be small actually. Okay. So we have a two case, alpha greater than 0 and alpha less than 0. So if alpha is greater than 0, so if we minimize this free energy, so let's see what happens. Uh, so del F del psi, yeah, so del F del psi will be 2 alpha psi, and this things are a little bit I need to always take into psi star. Okay, so whenever I am saying psi square, it is actually psi star. Okay, and then plus 4 beta by 2 psi square and psi star, let's say. So then psi star I can take common, 2 alpha plus 2 beta psi square equal to 0, and we already assume that beta is always greater than 0 and alpha is also greater than 0. So that means this term is always positive, right? Because psi square is again a I mean it's square of something, so it has to be positive always. So that means psi star is 0. Similarly, when you similarly you can just take del F as del psi star. Again you will get the same conclusion that psi equal to 0. So psi star equal to also 0, psi is also equal to 0. So that essentially means your psi square is identically 0. So your order parameter is 0. Okay, order parameter is identically 0. Now, so in this, so this case doesn't, I mean, concern us because if the order parameter is 0, then the whole free energy itself is 0. That means you are in normal regime, not in a superconducting regime. Now, this case can be interesting, actually interesting. So, alpha less than 0, but beta greater than 0. Sorry, alpha is less than 0. So, now if you take derivative del psi, then you will have alpha. Uh, Actually, here there will be not be any 2. It doesn't matter though, but yeah. Okay, so alpha we have psi star, let's say. So let me take. So del psi alpha plus beta by 2 and psi square, and then another psi square I am writing as psi star. Okay, so this means we will have alpha psi star plus beta by 2 psi square, and then psi star. Yeah. Or we can also simply take f to be without thinking so much things. We can also simply say that it is psi square and plus beta by 2 uh, psi to the power 4, and then we are taking the derivative with respect to mod psi itself. Okay, that is much easier to think. Again, we are not into the exact mathematics, rather the physical implication that will have. So we can simply write 2 alpha mod psi plus 4 beta by 2 mod psi cube. Now, if we minimize this, so for minimum of minimum f, we have del f del psi equal to 0, right? So if we put this thing to be 0, then we'll have 2 alpha mod psi plus 2 beta mod psi cube to be 0. So again we'll have psi, so alpha plus beta equal to 0. So you have three solution, actually two solution from here. One is psi equal to 0 and another in is mod psi square equal to minus beta by alpha. Okay, so these are the two solutions, and then of course you will get so actually it will be other way around, so it will be alpha by beta. So you will have mod psi equal to root over minus alpha by beta. Remember, we are in the case where alpha is less than 0 and beta is greater than 0. So that means if alpha is itself less than 0, that means we do not have any problem, because under the root it is overall positive. Okay. And you can actually check that, of course, if you take this case, free energy itself is 0, and then if you take this case, then free energy will have some value, we can actually determine. So it will be alpha mod psi square plus beta by 2 mod psi to the power 4. If we put this part, then alpha, so mod psi square means minus alpha by beta plus beta by 2. Mod psi to the power 4 means alpha square by beta square. Okay, so f will be uh, minus alpha square by beta plus alpha square by 2 beta. So this is minus alpha square by 2 beta. Okay, so this will be the free energy whenever we take this side. So what this necessarily means is that, so I'll have three solution actually of F. So this is free energy versus, let's say, mod psi. So so the solutions are, again, looks like something like this, where I have two identical free energy. I mean, yeah. So we have one case where free energy is exactly 0, and another two cases. So remember, this was a third order equation, third order in psi. So we have a three solution. So one is this particular exactly 0 of the free energy, and then for the other cases of psi, coming from here, we have a exactly two equal free energy. Okay, for this value, let's say uh, root over minus alpha by beta and minus root over minus alpha by beta. Okay, and this is not then mod psi, it is just the real part of the psi, because mod psi always have to be positive. So we have this solution where your free energy is minimized. So what this physically means is that once you are below Tc, so once your temperature is below Tc, then the system wants to minimize its energy by reaching in one of the two energy states. So this is one energy, and there is another energy, and there it can be anywhere. So here and here with equal probability. Okay, and this is the unstable equilibrium where free energy is itself zero. So yeah, that's the actually physical point. Now there are more important uh, I mean insights we can generate from this kind of solution that so so now see let's see what happens with psi, with the behavior of psi around Tc. Okay, so when T is near Tc, then how psi behaves with the temperature. And for that, we actually need to assume that alpha is some constant, or I can call it alpha 0. It's alpha 0, and it linearly behaves as Tc. Okay, okay. And then beta is almost equal to constant. Now these things actually I mean, so apparently, it might look like that these are not physically motivated. I'm just randomly assuming things that alpha has a form of like this around Tc, and then beta is almost constant. Actually, you can derive all of these things from a mean field theory. So in this course, actually, it will not be taught. But what we can do is if you consider the Ising model case. So again, I'll go back to the magnetization case because that's something I mean usually solved in statistical mechanics course. So if you solve simple Ising model in the mean field limit, then you can find that the energy you'll find the energy of the system. Okay, and if you expand the energy around I mean in terms of m, so there m is the magnetization uh, of the model, let's say, you'll actually so the energy will actually automatically reduces to this kind of term, that you'll have something and then T minus Tc. So this something constant, you will call it alpha, and then it will be associated with m0 square, and then I mean again another sum term m0 to the power 4, which will be almost independent of temperature. Okay, so these things actually can be derived from the mean field model. And the same thing can also be done here as well. If we solve the mean field, so if we solve the mean field model of superconductivity, but those things I think will not do here. So if we assume the alpha has this kind of form around Tc, and then beta is constant, then what we can infer is that mod psi, so mod psi in our case was minus alpha by beta. So this means that alpha 0 T minus Tc by beta, right? So this means that or I can make it plus by Tc minus T. Okay, okay. So this actually shows that around Tc, so if we have this mod psi and then T and somewhere Tc, this actually shows that at I mean at T equal to 0, let's say, you'll have some value. Okay, uh, so at T equal to 0, your psi will be constant, some constant, let's say, and then around Tc, it will actually behave as this square root of T. Okay, And this mean field is this Landau theory is only valid around this region. It's not valid here actually. Okay, so this is not valid. You cannot determine what will be my mod psi at t equal to 0. So this is not you cannot do it from the mean field theory. Landau theory, because Landau theory only assumes that mod psi is small, and which is only allowed around this TC, right? So you see that around TC it will be small. So, but around TC, what is the important point here is that it goes root of square root of t. Okay. Okay. So, and this is actually the characteristics of psi, and which has also been experimentally has been, verified that superconductivity vanishes at TC with a square root of temperature scaling. Now we can do a lot of things with it actually. Once you have this free energy, once we have the free energy in terms of this, let's say, so we had free energy expression some, yeah. So this free energy, and then we can determine the I mean uh, entropy of the system, and then once we get the entropy, so we can just take the derivative of f with respect to t, then we get entropy, and then once we get the entropy, then we can determine the specific heat. Okay, just you take another derivative of temper with respect to temperature of the entropy, and we can infer then that how entropy will behave with temperature, and specific heat will behave with temperature, and is there any jump in the specific heat, that can also be determined. Okay, but I'm not going into the details of this, because we'll see some of the assignment problems. Okay, so anyone have any questions or queries?
So by free energy, capital F, do you mean that the difference between the superconducting and normal state free energy,
Oh,
right?
yes, yes, that's a very good question. Actually, that's kind of always assumed, because when I write free energy for the superconductors, you can always add some constant value of this in the normal state, right? So this is
Okay,
for the
okay. Thanks.
superconductor, and then there will be alpha mod psi square plus beta by 2 mod psi to the power 4, and so on. Yeah. So this is always assumed that a constant value is already there for the normal state. Yeah. Okay. So any further questions? Okay. So this was the Landau theory, and what it misses is that it assumes that the order parameter for a superconductor is perfectly, it's constant, right? Spatially independent. So, uh, spatially independent, spatially do not vary. So what do we mean by that is that so this Landau theory assumes that mod psi is independent of any kind of, let's say, so this is a function of x, let's say x is a position of the of so we have a material, and we have, let's say, coordinate system somewhere x, y, and so on. It assumes that it depends on r to the power 0, essentially independent of r, some position r, let's say, right? And to go beyond this, we need Ginzburg-Landau theory. And Ginzburg-Landau theory, it assumes that it doesn't assume that it is independent of position. Rather, it takes into account of the spatial variation of psi, and then we can construct other things actually. For example, so there will be a first equation of Landau-Ginzburg, uh, and then second equation of Landau-Ginzburg theory, and so on. Okay. So let me have a look at the, assignments, and then if the assignment questions are sort of, all from the classes, then I can solve the Landau-Ginzburg theory as well, because I think it has not been fully derived, but yeah. But if you have any question, please ask. Okay, so let me see. Yeah, so the first question for the assignment 3 is that consider a homogeneous superconductor. Order parameter is independent of position variable. So essentially, we are in Landau regime, I mean Landau free energy. In absence of any external magnetic field B equal to 0, and then free energy near the transition temperature is given. So the question 1. So we have given Fs equal to Fn plus alpha mod psi square plus beta psi to the power 4. So here you see that there is no beta by 2, and beta by 2, this is completely kind of our choice uh, of calculation, because if we take beta by 2, you have seen that psi comes as root over alpha by beta, right? If you don't take beta by 2, then there will be an extra 2 factor 2 hanging here. That's the only difference. Otherwise, there is no uh, difference. Physics wise, there is no point. Okay, so then the question A asks what is the order parameter psi 0 that minimizes Fs? So that we have already solved. B is what is Fn minus Fs at the value of at psi equal to psi 0. So that again you can do. Okay. Okay. So then the question 2 is, so in the presence of external magnetic field B external, we just need to write down the first and second Ginzburg-Landau equation in terms of order parameter and the vector potential A that characterizes the magnetic field. So that means is that curl of A is magnetic field, and then we need to write the first and second Ginzburg-Landau equation. Okay, so okay, so let me solve this question actually. So for Landau-Ginzburg theory, so in Landau-Ginzburg theory or Ginzburg-Landau, so the free energy is expressed as a functional. So it's a function of function. Okay. So psi is itself a wave function kind of thing. So, but then you are taking, if you are defining a function which is itself a, I mean, depends on this function psi. That's why it is called functional. Okay. And so this is written as, again, all are approximated. PQ bar. So you see the DQ bar is coming because so this Ginzburg-Landau theory takes into account of the spatial variation of psi. So we'll take alpha mod psi square plus again beta by 2 mod psi to the power 4. And this term, as we have, I mean, as the question asks, B external is 0, no, sorry, non-zero. So we also take into account magnetic energy. So B square by 4 pi, sorry, 8 pi, it will be. And then we also have 1 by 2 m star. M star is again the mass for the Cooper pair, so it will be twice the mass of uh, electrons. And then you will have term which is h bar by I gradient. So this gradient operates in the spatial space, and q by Ca square. Okay. So this is the complete, I mean, function of Ginzburg-Landau. What it does is that, of course, this has this old Landau part, right? And then we have magnetic field non-zero, so there will be contribution from the magnetic energy, and then there will be contribution because we are considering the effect of spatial variation, so this gradient term is there. So gradient term works in the R space. Okay. Okay, so again the task is same. What we need to do is that we need to minimize with respect to all the parameters that we have. So here the parameters are psi and E. If we have magnetic field to be 0, then again it falls back to the only parameter is psi. Okay. So before minimizing, actually, we need to simplify this term little bit. So although actually the question asks, you just need to write down the I mean equations of first and second equation of Ginzburg-Landau, but yeah, I'm deriving it. Okay, so if you can write the above term as t cube of r and then alpha mod psi square. So this part will be as it is. Then we'll write this term first, okay? So I can write h bar by I gradient star. So this square means we'll have I mean this particular term and then star of it. So h bar by r gradient minus q by ca and then times the star of it. Okay, this part is the yeah complex conjugate. So these are vector quantities. I think I missed psi. So there here should be psi. Okay, or rather it actually should go p. Yeah. So this is one operator and it operates on psi and then square of it. Okay. So then the second term would be plus. This usual b square by 8 pi. Okay, so we just have written these two terms. So first term and then so what we have done in the second line is that we take this to be star and then the this term. Okay, so let me write down. So I have h bar by I gradient minus q by c a, so all are vectors, and then star of it psi star. So here will be psi actually because there will be psi star and then the other terms. I mean the exact same term h bar by I gradient minus q by c a and then psi. Okay, so this I have written this part and times this part times again this part. Okay, So what we can write from here is that, let me write down this term first, 4 pi, sorry, 8 pi, and then 1 by 2m star psi star h bar by I, uh, gradient star of it dot. Okay. So what we have done here is that we have done partial derivative of it, sorry, partial integration of it, so that this term essentially effectively comes as a minus of it. Okay. So if you do partial of u v dx, let's say, or any parameter u v dx, and then you have one term. I mean, so let's say you are integrating this and integrating, after integrating this, let's say v delta, and then minus of u prime v delta, sorry, v tilde, and then dx, let's say, and this boundary term vanishes. Okay, psi at plus minus infinity, it should always vanish. That's something we always do in quantum mechanics. So we use this so that an extra negative sign comes. Okay. Okay, so now we can write, uh, so these two terms can be arranged, these two terms, and then finally we can write as dq bar alpha mod psi square plus beta by 2 mod psi to the power 4 plus 1 by 2m star psi star. So we'll have psi star here and here. So, and then we are essentially taking this part and this part. Okay, h by so square again. So this I think I missed this. Okay, so this we can write as a star, but it doesn't matter because A is a real quantity, so you take star of it. It's essentially same. So what you will have is that you will have this part to be common, and you will see that a star of it comes here using this part and this part, right? And then again you will have something A and A star, which will be again A square. So that's what we did here. When you write again square, and then there is psi. Okay. And of course, we had b square plus 8 pi. Okay. All of this effort was done just to write, I mean, just to simplify this particular, so this particular format, just to take out psi and psi star from this term actually. Okay. Otherwise, rest of the terms actually we already solved this part, but then if you have this particular way of writing, then the minimization is feasible. So then again the same process, you just need to minimize the energy, free energy with respect. So again, I have not written that F0 part actually, okay? So F0 is the free energy for the normal state. So if you minimize with respect to, let's say, psi, then or for that matter psi star, So what we'll get is that 1 by 2m star gradient minus q by ca square psi plus alpha psi plus beta mod psi square psi equal to 0. So we have taken derivative with respect to psi star. So this is the minimized so del f del psi equal to 0 if when you take derivative with respect to psi star. Now taking derivative with respect to a, it's sort of a little bit tricky. So this was for the case, one part of the problem, because f was a functional of, f is a functional of psi and a. So with respect to psi, we have taken this and minimized it, means it is 0. Then we can determine what will be psi. Now the second point is del f del a. How do we derive that, right? So we need to put 0 and then what will be the expression of del f del a. So for this, what we assume is that a has a we can write as a0 of r, let's say, and then a0 of r. Okay, so what we are essentially assuming that a has a value of r, let's say, which is kind of almost constant. It has a on constant part, or the dominant part a0 of r, and then around this a0 value, and there is a variation depending on the space a0, small a0. Okay, that's what we are assuming. Now what we'll do is that we'll express the functional as, again, psi, and then this a0 plus a, I'm not explicitly writing the r's, so it can be written as f at psi and a0 plus so d q bar so you have h bar by I gradient minus q by c a0 uh, psi star dot minus q by c a0 psi plus 1 by 2m, again star, minus q by ca psi star psi, and then there will be so one particular term which will look like curl of a0 dot curl of a small a0. Okay. Okay, so how we can arrive at this is very simple. It just involves algebra. So this is what we have, and we will write a, capital A, to be this. Okay, a0 of r plus small a0, and we will assume that a0 is much smaller than capital A0, so that here if you see this expression, it is only expanded up to linear order in A0. I'm not writing A0. I mean, small A0 should be there everywhere. Yeah. Okay. So only linear in A0 terms are written, and then there will be, of course, order of A0 square. But those will be very small. And of course, when you do this part, you will get the free energy as a function of psi and capital A0, just like this. So this will be, so you will get exactly this term as a function of A0, and then around that it will have some, I mean, contribution from the small A0. Okay, and we are restricting ourselves to linear order in a small A0. So this part is just algebra. Okay, so now we need to use this, for this part we need to use some vector identity. This part you can use, this part will be A0, small a0 dot curl of capital A0 minus divergence of uh, curl of capital A0 curl of A. Okay. Okay, so let me just write down. So this was, let's say, 1, 2, and then this part is 3, and this is just a side note. So how do I arrive from equation 1 to equation 3, let's say, right? Okay. Now finally from equation 3, so this equation 3, so from equation 3 we can write simply, so f of psi of A0 plus A0 can write as, so this will be capital, and then dq bar so star of it, and then psi my should be plus psi star dot A0 plus 1 by 4 pi curl of B0. So curl of B0 means it is coming from the curl of A0. Okay, so we'll have a curl of A0. So this can be written as curl of B0, right? Because curl of A0 is B0 dot A0, and then of course the higher order terms that we ignored. So this there will be that. Yeah. Okay. So this will be the free energy if you expand in terms of A, let's say. Now, how do I minimize the free energy? We minimize the free energy whenever this particular term associated with A0 will vanish actually. Okay, so with respect to A, we essentially need to take the coefficient of A0 equal to 0. Okay, so that's the condition. Okay, so if you take this coefficient, that means this particular part, to be 0, then what you will obtain is the following. So again, so now I am drop the 0, drop. So essentially I am writing B0 as B. Okay, now so you'll get something like this: A Q H bar by 2m star C, and then psi grad psi star minus psi star grad psi plus q square mod psi square A plus curl of V by 4 pi. Okay, so this will be one of the minimization after this. This is the condition, and once you use the formula that in the Ampere's law, let's say microscopic form of Ampere's law, which says that you have a current whenever there is a curl of magnetic field. So circulating magnetic field will generate some current. So this, when you use this formula, okay, use this equation, then what we can get is that J equal to IQH bar by 2m star psi gradient of psi star minus psi star gradient of psi minus q square by m star c mod psi square A. Okay, so this is one equation of the Ginzburg-Landau equation. Yeah. So this is, let's say, I forgot which one is called first and which one is called second. Yeah, actually this is, I think, second. This should be second because it's associated with the A. Okay, so this is second Ginzburg-Landau equation, and then first we can get from minimizing the first minimizing the free energy with respect to the psi. So this was with respect to the vector potential A. This we minimizing with respect to the psi we already wrote somewhere. Yeah. So equation 2. So equation 2 is the first Ginzburg-Landau equation. So first GL equation. Okay. Okay. So this was the derivation of first and second Ginzburg-Landau equation. And then, so any questions? Okay. So let me move to the, yeah.
Hello.
Yeah, yeah, sure.
As far as the question number 2 of the assignment 3,
Mhm.
I think it is not
Hello. Yeah, I mean,
but I believe that it is always better to know the derivation, but it is not required, I think.
yeah, yeah. Question two doesn't require the derivation actually. Yes, that's true. Yeah. It just, yeah, it just says that you write those equations. Okay. Okay. Yeah. So the next question is, so question three says, assuming coefficient alpha to have a temperature using Ginzburg and so what you need to find is that assume alpha has a temperature dependence something like this, which we have worked with alpha and T minus Tc. Alpha is a function of T minus Tc. Oh, okay. So there is a typo, I think, in the question. So alpha of T should be alpha 0 T minus Tc. Okay. It is written in the question, it is written as alpha T minus Tc, but it should be alpha 0. Okay. So then, using Ginzburg-Landau equation, find an expression of coherence length. So xi t is what? Okay. So so we had first Ginsburg-Landau equation, something like this. So this was the Ginsburg-Landau equation, right? So I'll use this one. Okay. So nothing is mentioned in the question. That means we will always take B to be 0. Okay. So if there is no mention of magnetic field, then you will always assume that magnetic field is not applied. Okay. Anyway, superconductivity and magnetic field are sort of inverse. I mean, they do not like each other. So once you apply magnetic field beyond the threshold value, uh, it just superconductivity gets destroyed. So in absence of magnetic field, that means A equal to also 0. So we'll have 1 by 2m star. Uh, then so this h bar by I square, so it will be simply h square and then Laplacian and psi plus alpha of uh, psi, let's say, plus beta of mod psi square psi equal to 0. Okay. Okay. So, so again, for simplicity, we will we will consider the 1D case. So simply assume 1D case so that, okay, so I missed a minus sign. Yeah. So then we'll have equation like this, h square by 2m star del 2 psi del x2, or for 1D, you can also write as d dx2 plus alpha psi plus beta psi square psi, right? Now we have this alpha is alpha 0 T minus Tc. So once you below Tc, that means you are in the superconducting state. That means it is uh, minus, right? It is less than 0. So this we will write as minus mod alpha. Okay, so this part. So then we'll just use some scaling. Uh, so we'll have h square by 2m star alpha, actually mod alpha. Let me write down the steps. Now define. So our goal is how does I mean what is the coherence length, okay? And for coherence length we need to know how I mean psi behaves as a function of x, let's say. So you have a I mean superconducting material and how this particular wave function behaves. From there you can actually determine the coherence length. Okay, so we'll define this part h square by 2m star alpha to be and remember that, okay, actually let me define the mod alpha part. Okay, so this particular part will be minus h bar square by 2m star minus of mod alpha, right? We just use this one. So this means it will be h square by 2m star mod alpha, and this we take so this is positive, we'll take it as a xi square. So xi is some dimensionless parameter, let's say, and it's not dimensionless, but it's some parameter. And then we'll also write for this part, we'll also write beta by mod alpha psi square to be some function, okay, f square. So using this, so we can write this expression as minus xi square uh, so let me derive actually. So this particular equation can be written as xi square del 2 psi del x2 plus psi uh, so this will be minus uh, beta by mod alpha psi square psi equal to 0, right? Now, so what I need to do is that I am trying to write things in terms of xi and f, right? So I'll write psi, I'll convert psi using this equation, and also write I mean the del x, I'll convert it to del zeta, okay? Or not really actually. No, this part will be there. I don't need to do this. But yeah, I'll convert psi to f actually using this particular form, okay? And if you do this, then the form we'll have is xi square f double prime. F double prime means del x to del f, okay? And minus f plus f cube equal to 0. So I am skipping 2 3 lines actually here. From here to here you need to use uh, I mean this particular conversion from psi to f, and then we'll multiply by f prime. Zero, okay? Now this particular part can be written as d dx of minus f prime square xi square by 2 minus f square by 2 plus f to the power 4 by 4. Okay, so you can just go back here. So if you take simple derivative, then you'll get back here. Okay, so this means that this particular part is constant, right? Something's derivative is 0, that means this is constant. Now we need to use the boundary condition that f prime uh, almost goes as 0 far from the boundary. So when you are deep inside the material, suppose you have a superconducting material, and then uh, deep within the boundary, your I mean the wave function is essentially kind of smooth or constant. So what really happens is that around this boundary, your superconducting wave function is 0, right? Because this is let's say air or a normal material, then your superconducting wave function is something positive. I mean, it gains some value, and then somewhere deep within the material, it is actually 0. Sorry, it is actually remains constant. It doesn't vary much. So that is the assumption we will take, that once you are deep within the material, so far from boundary, will have a prime equal to 0, because you have a essentially a constant I mean wave function which doesn't really depend much on the x or position. So that means the derivative will be 0. So if your derivative is 0, then you'll have f square equal to 1. Okay, and if f square equal to 1, we can write that mod psi squared, the definition we used from this one, beta by mod alpha psi square, it will be mod alpha by beta. This is the rewriting of it. Okay, now using this, so using this part and this, so what we have is okay, yeah. So from this equation, let's say we have minus xi square f prime square by 2 minus f square by 2 plus f to the power 4 by 4 to be constant. Okay, okay, so from here, how can I get so if I simplify this, this will be xi square f prime square, and then plus f to the power 4 by 2 equal to some constant. So there will be minus I'm missing something actually. So I'll actually get this kind of equation. Uh, so I'll finally get half of 1 minus f square. Okay. So that will be my final equation. And after this, so I need to derive this. Okay. So I'll derive and upload. So this kind of function has a standard solution where f will be equal to tan hyperbolic of x of root 2 xi. Okay. So then from there, you actually, so using this, you will get back to the psi. So using again this expression, size, sorry. Uh, so this expression. So we have f, and then we will go back to the psi wave function, and then will function will come as mod alpha by beta to the power half uh, tan hyperbolic of x of root 2 xi. Okay. So this tells us, okay. So from this we can determine actually xi of t to be, so what was the question actually? So our question was the expression for the coherence length. Okay. So then we'll find that coherence length will be proportional to the 1 minus t by tc to the power minus half. And there will be of course some constant factors, which is h bar square by 2m, and there will be tc, yeah, and I think alpha 0 part will be also be there. Okay, m alpha 0 tc. So this we can derive actually. I'll derive fully and then upload. Okay, so the next question is, there are a lot of questions today. So question 4 is present schematic plots of order parameter, flux density, diamagnetic energy, and condensation energy at the normal metal junction. Okay, so this is just the plots we usually, see order parameter will, this is, let's say, normal region and then superconducting region. So what is asking is that we need to, I mean, calculate the order, just draw the order parameter. So order parameter will be 0 in the normal region, and then somewhere that will be constant in the superconducting region deep within the superconductor, and then flux density. Here is a function of distance. Okay, so flux density as a function of density. I don't know how it will look like. We'll see this. Then the fifth question is actually full description of electromagnetic radiation. So it's a description of full experiment actually. And then sixth question is again same, the experimental uh, explanation of ultrasound attenuation. Seventh is also actually the similar thing. Okay. Okay, actually flux density, yeah, flux density it will go as flux density means effectively you can think of like how much. So I'm again back to the question 4 actually. So how magnetic field will sort of penetrate the normal superconducting region. Okay, so this will be just, so if you have a normal region and then superconducting, so somewhere in the normal it will be finite, of course, and then it will actually vanish quickly in the superconducting region. So this will be flux density. Okay, and then so another question was in question 4, what was the diamagnetic energy? How will they look like? So again, I have a superconductor normal region. So this is, let's say, normal and superconducting region. So at normal metals are not really a kind of diamagnetic, or even if they are diamagnetic, their susceptibility is very small. Whereas we have seen that for superconductors, they are perfect diamagnet, right? Susceptibility is exactly -1. So so it will have a something like this. The diamagnetic energy is given by hc square by 8 pi, or we are writing b square. Okay. Okay, so that is for question 4. For normal also, it's not, I mean, absolutely, so they are not diamagnetic, but the perfect magnetism is shown in superconductor. So this will be perfect BC square by 8 pi. Okay, so the question 8, explain S versus D wave superconductor, I mean D wave order parameter symmetry. Okay, so question 8 says, and then write down the BCS gap equation for D wave symmetry, and you don't need to solve the equation. Anyway, you can solve the equation. So for S wave superconductor, actually gap equation was, I mean gap. So we had a Fermi surface, perfectly spherical Fermi surface, and then the gap was actually constant, right? Because we have also taken V equal to V0. So interacting potential was constant. So we had a uniform sphere, and then the gap was uniform everywhere. So basically, gap is independent of K. So we had a uniform gap. So when independent of momentum. So when the gap is independent of momentum, that means it is also the independent of energy. Okay. But for D wave superconductors, we have some nodal points. So let's say this is X and Y. So around the corner, actually, it will vanish. So D wave superconductor will have something like this. So it has some momentum dependence, so that it is not independent of momentum and as well as energy at some particular momentum point. So this particular points, okay, the superconducting gap vanishes. So delta is a function of K here in the D wave. Okay, and then we need to write the, I mean, D wave uh, gap expression, which is just as it was written in the class, which is simply 1 equal to V0 sum over K prime f d square of K prime by 2 energy at K prime, and then tan hyperbolic of beta ek prime by 2, right? Where ek prime is again the delta K prime. Now in this case delta is K function and xi K prime. Xi was free particle energy actually. Okay, and what we had is that V at was a function of K prime. It is not, it is some constant phi 0, but then it also dependent on K. Okay, okay. The next question is uh, so write down the TJU model in the second quantized notation and explain various terms. Write down the Hamiltonian in K space and extract interaction term that we can facilitate a pairing between electrons needed for superconductivity. Okay, actually this problem was exactly solved in the, actually not solved, but it was done in the class, up to which we can sort of analytically proceed, right? So TJU model is simply, will have a hopping term. So T implies simple hopping term, and then J is some spin-spin interaction or a Heisenberg spin interaction kind of, and then U is Hubbard interaction. Okay, and then the 10th question is list out a few stoichiometric compounds that yield transition temperature larger than 50 K, basically unconventional superconductor, for both copper oxide and iron-based family of superconductors. So there's a pretty complicated name, I think. So for example, for Cu based superconductor, we will have CuO2 based cuprate oxide. So we'll have something like Bi2, Sr2, uh, CaCu2O8, and I think this has a critical temperature of around 85 Kelvin actually. Okay, so most of the other superconductors have TC around 25 Kelvin. In fact, graphene-like system usually have TC at sometimes it is millikelvin or maybe Kelvin, not more than that. But there are metallic superconductors which have TC like 25 Kelvin. And then there are other cuprates, for example, so from other family like Ag, Ba2, CuO4. So this has even higher temperature, I mean TC 94. And Fe iron based, there are quite a few. So for example, Nd, Pe, As, uh, so we'll have some 0.89, I think. Yeah, 0.89, and then iron is 0.11. So again, this the TC is 52 Kelvin. Okay. Okay, so actually most of the question are from the class itself. Yeah. Okay, so any questions? Okay, so if not, let me stop.
Can you
Yeah,
can you repeat?
yeah.
Hello, can you
Please.
repeat once more the copper oxide based superconductors name? I don't. I mean, I
Yeah,
missed out
so
that.
these are pretty, I do not know even the name scientifically what is called. So Bi2, Sr2, Ca, Cu2O8. Okay. And then there is another Ag mercury based Ba2, CuO4. So there are many other actually, yeah. So I think highest cuprate based highest transition temperature we got around maybe 110 or 120 Kelvin. That's the maximum. But there are other superconductors where you can actually pressurize the material very high level of pressure, gigapascal or more than that actually. You can have very high temperature. It even people claim that at least it goes till 200 Kelvin and so on. some years back there is a claim that they got room temperature superconductivity, but yeah, there is no substance in it later on. Okay, so any questions? So if not, let me stop here.
So what about that question number 9? It is a U model.
Oh, TJU model is actually so it says that you need to write the Hamiltonian in the second quantized notation. So that I can actually write. You anyway cannot solve actually TJU model even. And then it says that write down the Hamiltonian in K space. And do you see the DOA pairing term? And of course the exact interaction term that it can facilitate pairing between electrons. Okay. So TJU model is, let's say, Hamiltonian. I will have some hopping term. Uh, so usually we write hopping with minus t. Uh, Again, we only take nearest neighbor. Sigma is the spin indices. So Ci dagger, some sigma, Cj sigma, and plus Hermitian conjugate of this term, plus, so this becomes the t term, and then the j term, spin in spin interaction, sum over again ij nearest neighbors, si dot sj, uh, minus ni nj 4. So ni nj is the number operator, okay, for the ith particle. So ni is simply ci dagger ci, and similarly for j. And then u term will just be again number operator, but with specific spin consideration, ni down. So that's what you need to write. So yeah, so this part is hopping, this part is exchange, and this part is on-site potential, on-site data. Okay. In K space, you can write the Hamiltonian also. So what you need to do is that you need to go from Ci sigma to Ck actually. Okay, so you need to do Fourier transformation, and then you can write the Hamiltonian in the Fourier space. So I think the last lecture is fully based on fully solving this problem as much as we could do in analytically actually. Okay. So then you will have a sum over k sigma. So site index is 1 because you are essentially in the continuum limit. You will have some epsilon k coming from the hopping. This is the dispersion. And then ck sigma dagger, ck sigma plus, let's say, so here there will be lot of terms. Uh, so of course k and k1 and k2 will be there, and then there will be spin indices which will denote by alpha, beta, gamma, and mu, let's say. And the assumption is that alpha is not equal to beta and mu is not equal to gamma. Okay, so then we have j q by 2, and then minus delta alpha beta delta gamma mu c k1 alpha. Alpha and beta are the spin indices. It can be up and down. C k2 beta c k2 minus 2 mu, and then sorry, k2 minus q, and then spin indices is mu, and then we'll have c of k1 plus q gamma. So this was the exchange term, and then the about the interaction term will be k1 k2 q c k1 of so this will be the in the momentum space where your epsilon k is simply square lattice, this person kxa plus cos of kya, and then jq will be j cos qxa plus, yeah, that's it. And the interaction term will be v of q minus 2j of q, okay, or j of q we're writing. Okay, so here actually you can, I mean, so this cos qx and qy are actually can be written as, so this part cos qx and qy will be written as I mean in expansion of kx and kx prime, so that so there will be term something like cos kx uh, minus cos ky, and then cos kx prime minus cos ky prime. So this will be part which will be like d wave pattern. If you plot in the kx ky plane also you will see that. Okay, but this is the full I mean this was one of the lectures actually where it has been solved. Okay, uh, is there any question? I mean, some raised hand. Hello, and any questions? Okay, so if not, I
Can
will.
you can you
Uh,
hello?
yeah,
Can
say.
you please show me again once again the BCS gap equation for D wave superconductor? The question number 8.
Mm-hmm.
Just
So this part actually. Okay.
okay. So one left hand side is
Yeah,
1 equal to
just similar to the S wave case. So initially what we studied
uh,
was S wave without saying it. S wave because it has a perfect symmetry of S wave like. So these things are named like orbitals. We have a S wave orbital which is perfectly symmetric, so it is called S wave. And then there is something called P wave, right? So P wave we had either Px is like that, and then depending on that axis you choose, Py will be like this, Pz will be like this, or again, so that will be the P like, and then D wave we had something like this, right? Four lobe. So those things are named as per the electronic orbitals. Yeah. So any questions?
And can you please just show the second part of the question number 9?
Second
I'll
part of
just,
the question number 9.
yeah, I mean that interaction part. I will just take a screenshot. Please. Thank you so much.
See, I'll upload this actually. Okay. Yeah. Okay. So we can stop here, I guess. Yeah. So I'm ending the
Hello.
meeting. Yeah. So sorry, any questions? Hello. Yeah, Aryan, you had a question.
No, sir.
Okay. 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 So then I'm ending the meeting.